Hi, so my presentation is about using the graph theory to conduct remote sensor image segmentation and classification. At first, I will briefly introduce my study. Remote sensor images has been widely applied in urban landscape studies, but the traditional method use the pixel level remote sensor images to classify land uses. This can bring inaccuracy in capture the um, urban patterns because remote sensor image is strongly spatial dependence, and in general, people want to use that spatial dependence to conduct urban analysis. But the pixel level images will have lots of noises, and this will bring inaccuracy in the classification. So recently, graph theory has been widely applied in solving computer vision problems, and I'm wondering if I can use some graph theory to find the spectral communities of image pixels and then classify them into different LED uses. So here there's a problem. The problem is that how I can apply graph theory into data with strong spatial dependence, because in most cases, people use social network data to conduct graph analysis. But here I choose data with I choose image as my study as my data source, and I want to conduct some graph-based study on images. Therefore, I read some literatures about how to using graph theory to do image segmentation. The first paper I read is the paper Professor Wu uploaded in eLearning. So in this paper, they developed an efficient modularity-based segmentation algorithm. So in their study, homogeneous patches in the image were viewed as communities, and Lewis method, a modularity optimization approach, was used to find the maximized community groups. So in general, the image was first initialized into a set of superpixels, and afterwards, the Lewis method was applied to find the modularity increase, find the largest modularity increase in each iteration, and at the same time, the similarity matrix was updated each time. And next, Wang developed an regional-based image segmentation algorithm based on k-means. So in their study, both spectral and spatial distances were used to constructing the adjacency matrix. So this would be a very useful information, because in my study, remote sensor images has a strong local connection, but the global connection is relatively weak. So later on, I read another paper. So Achanta in 2012 proposed a linear iterative clustering algorithm. So in his algorithm, the image can be segmented into several large pixels. Those super pixels can group similar pixels into the same community. But more importantly, this approach can greatly reduce the computational burden and improve the computation efficiency. So this is the overview of my study. At first step, the first step is image pre-processing. So in image pre-processing stage, first I choose 3 bands from remote sensing images. Band 543, because these 3 bands can better reflect the true color of the landscapes. And also I convert the image from unit 16 to unit 8, therefore it can be better displayed under Python. The image data I used comes from the USGS website. It's all free access. It's Landsat 8 remote sensing imagery, so it's very convenient to download it. In step 2, I apply the superpixel based algorithm to do the superpixel segmentation, and I got several large superpixels. In the step 3, based on each superpixels, I constructed a graph structure by calculating the adjacency matrix. So in constructing adjacency matrix, I use both spatial and spectral similarities to find the local connection for each pixels. In step 4, a community maximization-based approach, Louvie method, was applied to find the best community structure for best modularity structure for each superpixels. And in step 5, I construct a sequential neural network using Keras to classify each segments into different LED uses. So next I will talk about methodology. So first I will talk about graph-based image segmentation. So for graph-based image segmentation, people usually represent image as an undirected pairwise graph. In the graph, each node corresponds to a pixel in the image, and each edge connects a pair of neighboring pixels with a weight parameter. In 2006, Newman defined modularity as the following function. So in this function, Aij is the adjacency matrix. Ki is the degree of nodes. So in order to calculate the modularity of the graph, first this function will be calculated iteratively to find the matrix Q, and then applies the eigensolver and then solve the eigen problem of matrix Q. Find the largest eigenvector. For eigenvector with value larger than 0, it's one group, and for other for value in other group, it's another. For other values, it's another group, and this process can be conducted iteratively until all values in the eigenvector is negative. So next is the Louvie method. Louvie method is a modularity optimization method and widely applied in community detections. So it was defined as follows. In this algorithm, summation in is the sum of edge weights inside community I. Summation total is the total edge weights connecting to nodes in community I. And the Kij is the summation of weights from community I to community J. So after I applied the Louvie method-based segmentation approach, I also constructed a neural network to classify LED uses. The package I used to construct neural network is Keras. So Keras is a high-level neural network library under Python, and it was running on the top of either Sino or TensorFlow. In Keras, a model is treated as a sequence of modules, and each module is fully configurable. So in the sequential model I built, there are total of 3 layers, including an input layer, a hidden layer, and a sigmoid output layer. And the activation function for the input and hidden layer, I used the ReLU function. The ReLU function will enforce a negative value to 0, and this can solve the problem of gradient vanishing and exploding. So also it's computational efficient. This picture is the study example of my project. In general, this picture composites of 3 bands, bands 5, 4, 3, and the resolution for this picture is 30 meters. So it means each pixel represents a 30 multiplied by 30 square meters area. So the total size of this picture is 1108 multiplied by 805 multiplied by 3. So it's a very large graph network if we constructed it into if we build a graph based on this image. So because of the high computational demands for calculating the adjacency matrix and modularities, so initially parts of the image was selected, and my proposed method was applied to test the results. So the image on the left is the segmented results from superpixel algorithm. So in this algorithm, we can see that it can detect the larger boundaries of landscape features, but it still failed to capture lots of small urban patches in each superpixels. But after we applied the Levin method, and the results is showed in the right. So in this picture, it can capture lots of small urban patches, because it optimizes the modularity based on the modularity increase. So actually there is a trade-off between the remote censoring classification and remote sensor image classification, because if we choose larger segments, the results would be not accurate. It cannot reflect the true landscape features. It will ignore lots of small urban patches. But if we apply the individual pixel-based approach, this approach will also bring some inaccuracy, because it brings too much noises and cannot be applied for urban landscape analysis. So in this study, I used the superpixel algorithms to adjust the superpixel size, and then applied the Levin method to detect the smaller communities. Therefore, by first applying the segmentation algorithm to get the segmented communities, later applied the neural network classifier, I got the classification results. So the training data for my neural network is coming from my personal identification. So I identify the land use types of some urban feature, some urban patches by myself. It's about 200 or 300 individual urban patches. Then I trained the model. So based on the same training model, I classify the total ladder uses for different approaches. The first one is the super classification results based on superpixel algorithms, and the second is the classification results based on Levin method. So from these two pictures, we can clearly see that Levin-based method can classify ladder uses into with a better results because it captures the more detailed urban features. But that's not enough for our evaluation. So in order to compare my results, I also compare with the ladder use classification results from Fuzzy's Warp-based algorithm because it's still very difficult to have access to the true ladder uses in this specific study area. So here I just apply the Fuzzy's Warp-based algorithm and classify the algorithm to segment images into multiple patches and then classify them into ladder uses and compare my results with Fuzzy's Warp-based results. So there are two approaches I choose to evaluate the model. The first one is kappa coefficient. Kappa coefficient is calculated from kappa error matrix, and it's been widely used to access the accuracy of remote sensor image classifications. And overall, if the kappa coefficient is above 0.75, the results would be excellent. So in my results, the kappa coefficient is 0.86, so that is acceptable for the ladder use classification. Another approach I used is ROC curve. So for the ROC curve, it's widely used in the binary classification systems, and the process is by changing the threshold value from high to low. So the threshold value is the probability of the classifier, prediction of the classifier. So by changing the threshold value from high to low, true positive rate and false positive rate can be calculated by comparing the predicted value to the cumulative real values. And the area under curve is the statistic to reflect the results, the goodness of the results. And in my studies, IUC is 0.85, which is also not bad. So in this study, I applied the Levin method to maximize modularity of remote sensor images. And in order to improve the processing efficiency, first I applied the superpixel-based approach to segment superpixels into to segment images into superpixels, and later on, adjacency matrix only consider local connection, and the spectral similarities was applied to construct the graph, and the Levin method was used to group each superpixel into many smaller urban patches. The classified result shows that my results is acceptable and can be further studied as a algorithm for remote sensor image classification. However, there are also some problems with my study because the spatial resolution of the data source, the Landsat 8 data is 30 meters. The resolution is 30 meters. So this study only provide a general approach for ladder use classification. And more specifically, if we can incorporate in more spectral bands will reflect more detail, more landscape features, such as some plants features. Or or if we can have access to high-resolution remote sensor images, such as 2 or 5 meters. So a much more detailed landscape features can be captured by this algorithm, and I believe the classified results would be more richful and have more meaningful application. So that's my presentation. Thank you so much. And for all files in this project, the report was written by LaTeX, and all LaTeX files has been uploaded in Dropbox. And also, the the codes can be divided into 3 parts. The first part is the segmentation part, and the second part is the neural network part, and the last part is the evaluation part. All those codes were uploaded into Dropbox, which can be found with the link below. So thank you so much.